Welcome to part one of I don't even know how many it's going to end up being videos on Earth structure and Earth systems. So, this is going to be one of two mini units for our whole big chunk of Earth science. The other part is going to be on earthquakes and volcanoes, but we'll worry about that later. So, Earth structure and Earth systems, it is not a specific chapter in your textbook because I kind of sort of stole a bunch of sections from 3 different chapters in your book, which is one of the reasons why there's not a nice pretty PDF online yet, because I have to still create it and make sure I steal the right sections for you. But this one on Earth structures and systems should be pretty easy and simple. There's a good chance you've heard a lot, if not most, of this before. And it's going to talk about how the Earth was formed, geologic time scale, layers of the Earth. It's going to talk about plate tectonics, continental drift, and pretty basic, simple Earth science stuff. You guys should have some awesome grades with it. You have 30 vocabulary words. I decided to break it up and shift some of the words around. So you've got 30 vocabulary words that go with this. They are already on Google Classroom. Hopefully you've looked at them. But let's go ahead and get into this. Okay, so what you see before you is part of what's known as the geologic time scale, one of your vocabulary words. And it's going to lay out pretty much all of Earth's history before us, and it's going to get categorized. However, I am going to make you memorize part of this. Don't worry, it's not going to be as bad as the electromagnetic spectrum. This should actually be much easier. I am going to make you know the eras, okay? And the eras in this geologic time scale are going to be the Cenozoic era, the Mesozoic era, and the Paleozoic era. Now, the Mesozoic is one you're probably most familiar about because a lot of kids were interested in dinosaurs at one point. So this is where dinosaurs were roaming around. You've got the eras here are broken into smaller sections called periods. So the different shades of green, blue, and purple are showing you the length of each of those periods within the eras. So you have the Cretaceous period, the Jurassic period, and the Triassic period. And yes, this is Jurassic like Jurassic Park. Fun fact, the T-Rex in Jurassic Park shouldn't have been in Jurassic Park. It should have been in Triassic Park, but no one ever made that movie. So, you know, Hollywood. I am not going to make you memorize all of these different periods, okay? Don't stress out about that. You just need to know Cenozoic, Mesozoic, and Paleozoic. And you also need to know how to read this, because this says time in millions of years ago. Down here on the right, you've got 570, and over here on the left, you've got 0. So you kind of read it backwards. This is present day. We're in the Cenozoic era. So as you go down the line here, that's going to be putting you farther and farther and farther back in time. So this chunk here that says Precambrian, this is not an accurate representation of how much time the Precambrian era took. Okay? Precambrian time is a huge chunk of time, which this next slide is going to show you. See how small the Cenozoic, Mesozoic, and Paleozoic eras just became? This whole chunk here is Precambrian time. So the previous slide is just zoomed in to kind of show you the periods being part of the eras, but this second slide is going to give you a better idea of how old our planet is and how very little of it was populated by the organisms that you are familiar with. And looking at this one, this is time in billions of years. Okay? Not even millions, billions. The most accepted number that I've heard for many years as far as Earth's age in science is 4.6 billion years old. And that's going to be the one that you see in your textbooks a lot. That's going to be the one that I think that pops up on your test at least once. Maybe even be a bonus question. Can't remember. I'll have to double check. But that is the age you're going to see most often. So on that note, let's go ahead and jump into my TED Talk on this. We've not shied away from talking about some controversial issues in my class. We've discussed the Big Bang Theory, and later on down the road, we're going to talk about evolution. So let's talk about how the Earth was formed and how old the Earth is, because for some people, those can be hot-button issues. The good news is that regardless of whether you fall on a very religious side of this or a very non-religious side of this, you're going to be asking the same questions and having to deal with the same evidence. So kind of let me explain and break that down. If you're on a very religious standpoint, you've probably heard the earth is between 2,000 and 5,000 years old, which this whole 4.6 billion year thing doesn't match up with your beliefs. That's perfectly fine. I think that we would agree that a few thousand years is still technically considered old to some people. I am considered old to some people. Yes, I know who you are. So, it's going to be okay. If, again, you want to look at the non-religious end of the spectrum, 4.6 billion years is old, okay? Is old. And I do apologize because I can't hit on some of the other major religions besides Christianity because I just don't know as much about your creation stories and ideologies about the earth. That's the main one that I know about because it's the one that I practice, and it's the one that most of the people in this area tend to go with. So I apologize for my ignorance, but it is not within my realm of knowledge. Let's keep going on this train of thought of looking at what we got here, okay? So, as far as how Earth formed, and again, with time, when we're trying to pinpoint the exact age of our planet, unless we had an eyewitness, we don't know. Okay? Unless there's a secret eyewitness out there that's as old as the planet and apparently lava-proof as well, because they pretty much have to be. That whole picture that's the background of this PowerPoint is not the sun. That's an artist's representation of what early Earth may have looked like. We don't know. So, again, going on a religious side and standpoint of this, there's a verse in 2 Peter, which chapter 3, verse 8, that says that with the Lord 1 day is as 1,000 years, and 1,000 years as 1 day. That again tells you that there's no comparison when talking about time, because time is a man-made construct. It's not real. You've never seen a deer worried about being late to a business meeting. You've never seen a bird be upset because it slept in too late and it missed its bus or something like that. We are the only animals that are concerned about what time it is for the most part. And trying to condense an idea as big as God into human terms, we just can't. It's like trying to fit the entire ocean in a, fish aquarium. You're not going to do it. That's too much for our little brains to comprehend. Again, if you want to take religion completely out of the picture, you're still dealing with the man-made construct of time. Okay? It's not perfect. It's almost qualitative. It is technically a quantitative measurement, but it's man-made. And trying to apply that to something we have no experience with is difficult. Same thing with Earth forming. Those people that are on a religious end will say, I know how the Earth formed. On day 1, God spoke this into being. On day 2, this happened. Day 3. You're right. You know your Bible history. However, as he was speaking that stuff into being, what was happening with the atoms, the molecules, the compound, the matter that was in space? What was it doing? How was it physically forming itself to obey what was being spoken into being? You don't know. If you're on the non-religious end of the spectrum, you still don't know. So you have the same questions here of what was going on in space with the formation of our planet? What all collided and coalesced and formed what we have now? Where did that matter come from? We don't have any rock-solid proof and evidence. Okay? So, again, regardless of which end of this spectrum, or even if you're in the middle of it, and you're agnostic, we're still all clueless here. Okay? We're just taking the best guess with what little tiny data that we have. And with this whole Precambrian time, which is going to be the youngest and earliest of times, we have very little evidence. 88% of our history, and we have so few fossils from this time. And we'll talk later in this chapter about how even our fossil record isn't perfect by a long shot. Okay? Our fossil record, it's the equivalent of an encyclopedia set that has been tortured for a decade by preschoolers The poor things have been used as coloring books. They've been made into paper airplanes. There was a paper wad fight with one of them. 2 of them got flushed down the toilet. Another one's buried on the playground somewhere. Little Johnny took one home 4 years ago and no one's seen it since. The class pet nibbled like a corner off of 3 of them. They're poor, pathetic, broken, shattered, and very far from being complete like they used to be. That's our fossil record to an extent. We're missing some pieces. And later on in this section, we're going to talk about why we are missing so many of these pieces. But our evidence for what's going on is few and far between. Just remember, we have these 3 main eras, and they're the 3 most recent ones. I'm going to have you memorize again. The one that we are in right now, that we are existing in, is the Cenozoic. In the middle, starting also with an M, is the Mesozoic. And the one right before the Precambrian is the Paleozoic. Okay? So you've got those 3 eras, and I'm not going to make you worry about the smaller periods that each one is divided into. But I will tell you that they are vocabulary words, so make sure you know the difference between them. Let's talk about this early Earth, and what we think it might have looked like, how it formed and came to be. I want you to key in on one word, which is hypothesize, which is going to come from the word hypothesis. And I want you to understand the different rankings of things in science. There's 3 rankings. Bottom tier is going to be hypothesis. Middle tier is going to be theory. Top tier is going to be law. In this unit, it's going to be super important that you pay attention to whether something is categorized as a lower tier hypothesis, a middle tier theory, or if it made it all the way to a law. Okay? You can even relate it back to social studies that we're talking about right now, like a bill versus a law. Sorry, I had to. But hypothesis. With that being the lowest tier, this is an educated guess. Okay? It's not just some random something that's a shot in the dark. It's going to be backed and supported by a little bit of data, which is what made them make this educated guess, because you have to be educated, just a smidgy poo, in order to make an educated guess. Theory, on the other hand, our middle tier, okay? That is going to be what a hypothesis turns into when it is being tested and repeatedly tested, and the same conclusions have been found by multiple scientists in multiple countries all over the world for many years. It gets upgraded to a theory when all that data still holds true. And then lots of time and experiments and testing and testing and testing and data later, it can sometimes maybe graduate up to a law, which is the equivalent of a truth. A law pretty much is, this is a scientific truth, fact, 100% beyond a shadow of a doubt. This is going to happen this way every single time, which is why there's not a ton of laws in science, because very few things you can always be certain of. So this is a hypothesis. This isn't even a theory. This is somebody's hypothesis, okay? This is the moon was formed when a very early Earth collided with another object, which again is kind of, sort of, part of what you're seeing here in this background picture. Because if Earth looked like this, it's not exactly totally solid yet. That's a whole lot of magma-y, lava-y goodness going on there. And since that's sort of kind of liquidy-ish, if a large object collided with it, it could possibly knock part of that off into space. And gravity, since it pulls everything toward the center of mass, would again make it another secondary spherical object, like our moon. Logically saying these things out loud, yeah, that sounds like a complete total possibility that maybe, probably could have almost happened. We've got rocks collected from the moon from our Apollo missions that we've been able to use carbon-14 dating and look at radioactive elements and try to find their age. And if you look at their age, it's that 4.6 billion years old. So that goes back to the Earth and Moon being really, really close in age, which is why this hypothesis seemed logical and has popped up in your textbook. That is the explanation on how our moon came to be. They think that our planet began as a ball of dust, rock, and ice in space. Now, if that doesn't sound glamorous, I don't know what does. Congratulations, you're living on a giant ball of space dust. Yeah. So, you're probably sitting there thinking, how does that work? Well, let's think back again to gravity. Every single thing in our universe that has mass has gravity. So as gravity began pulling objects with mass together, their mass was increasing, which means their gravity was increasing. And when your gravity increases, you're able to pull more things towards your center of mass, and huzzah! We've got something as large as our planet, okay? Which is exactly what I've just said here. As Earth grew larger, its gravity increased, pulling more material into it, and when they collided, because, I don't know about you, but that looks like it's a little hot and roasty toasty to me, it was able to melt them and add them again to its mass, okay? The really, really dense stuff. We're going to talk about density a good bit in this chapter as well. The dense material is going to sink and form the core of our planet, and the less dense material is going to rise and help form our crust, which is eventually going to cool, and that's where we are. Okay? Again, sinking and rising. You need to think about this in 3 dimensions, 360 degrees. Because when we think sink, we just think stuff goes down. Well, remember, gravity's not pulling you straight down to the opposite side of the planet. It's pulling you to the center of the planet. That is the center of Earth's mass. So that's why it was able to form our core. All that dense stuff was being pulled to the very, very, very center in all 360 directions. And that's why our core is in the center of our planet. And the less dense material rose to the top in all 360 degrees. And that's why the crust goes all the way around the planet and we don't have any big, gaping, terrifying holes in it. Okay? So, our atmosphere is going to form next from volcanic eruptions and collisions with comets. Because comets, I believe, are about the equivalent of a dirty snowball in space. Notice I said snowball. Snowball means things that are very close to water being on them. So we have different elements being added into our planet here. And water, when it's made to steam, can lead to water vapor and all sorts of other gases being able to rise up, and some of those elements being trapped by Earth's gravitational pull and creating the many, many layers of our atmosphere. Now again, we have no proof of this. We didn't just sit and watch like some type of recording from back in the day and put all these people. These are ideas and speculations. Again, this is a hypothesis because if you read this, I mean, it sounds logical. There's nothing that I've come across so far in this that sounds completely Looney Tunes and bonkers yet. But it sounds very logical and reasonable, and it's based off of certain small things on Earth that we can even observe here. That is how these different things got trapped and create our atmosphere, which we are very, very grateful for because, we kind of sort of probably wouldn't be here, at least living anywhere near as comfortable of life, if we didn't have our atmosphere. Look at Mars, for instance. Mars has, like, next to no atmosphere, and it's not exactly as lush and pretty and, filled with life. Again, obviously, our surface, looking here, it was just a tiny smidge too hot for water to be there, okay? Because, I don't know about you, but when you set water on fire, it tends to not be water. Or, when you throw water on lava, there's like some steam and water vapor that ends up happening, as I mentioned before, the comets. So it's going to stay like water vapor in our atmosphere, but you can't be a hot, fiery mess, forever. Eventually our planet had to cool down as more of that less dense material rose to the top, started forming our crust, things started to chill out just a little itty tiny bit. And as Earth cooled, that means the temperature cooled enough for water cycle, remembering time, it to condense, and then for there to actually be precipitation, and it rain, and rain, and rain, and rain, and rain, and rain. You're like, just say rain about 300,000 more times, because whole planet, again, based on what little data we have, covered in water. Okay? We're going to have lots and lots of oceans. I think we can all agree. 72-ish% of our planet's covered in water. That's a lot of water. Okay? Whole lot of rain happening there. And during this early Precambrian time, most of the crust was able to cool and start creating our continents. Now, spoiler alert for what comes later in the chapter. Our continents weren't always where they are now. They weren't always shaped or looking like this, but again, that is another hypothesis or theory that we will discuss here in a little tiny bit. Let's break this down, and I know I'm blocking part of this, but it says, so why do we actually think this is true? Which is a valid question. Be like, okay, fine, so what? It makes logical sense, you know, it sounds good and stuff, but people make stuff up all the time that sounds good and logical and true. So why do I need to be buying into this? Well, here's where we've gotten some of our evidence from. Again, doesn't make it completely and totally right and accurate, but we at least do have some evidence trying to back this up. And now I haven't finished doing it to the whole chapter, but if you notice these little planet icons here, those are probably going to be things that come back to haunt you probably on test day. Just going to throw that out there. But geologists have drilled holes as deep as 12.3 kilometers into Earth. I know that number does not exactly sound impressive, but you know what sounds less impressive than kilometers? A unit of measure that you know because we're not on the metric system. That is going to be a whopping 7.6 miles we've drilled into the crust of our planet. Which again, probably does not sound that impressive. But think back to like when you were little and you decided that you were going to dig a hole and you were going to dig that hole so deep you were going to get to China. It didn't work out for you because you probably got about like a foot or two deep and you're like, I'm over this, I'm done with it. That is actually kind of fairly impressive to an extent. And during our drilling into the Earth, we've brought up many, many samples of rock. Why do we care about rocks? They're just rocks, right? They're dirt. Not exactly. So, think about it this way. Earth is in layers, okay? Not just like crust, mantle, core kind of layers, but even the crust has different layers that it's made up of because different things have been deposited on it and they layer up. So, the deeper you dig into it, the older it's going to end up being. So the deeper we dig, the older the stuff we get to dredge up with it. So these rock samples from deep within Earth are pretty useful for us to study because they give us little hints to the past, like what minerals were really prevalent, or if we're lucky and we hit some fossils, what type of organisms existed there. Okay? And they're studied. Volcanoes. Where does the lava come from that a volcano spits out? Inside the Earth as magma. So when magma goes through the volcano onto the surface and becomes lava, any of the rock that is jettisoned from it is actually coming from within Earth. It's coming from within the mantle. So it even went through the crust and actually got into like the mantle-y area. And that tells us some really cool information about the inner workings of our planet. So they're also useful in these studies of trying to figure out what's ticking inside of our planet. And they also, again, give us clues to Earth's structure and conditions deep inside our planet. These things happening tell us that our planet has at least two layers. There's a crust, because we're living on it. We see it, we touch it, we know it's there. And volcanoes tell us there's something a little more spicy and fiery down below, because it's going explodey boom, and we can also, again, see it. Don't touch that. And we know of it. Seismic waves from earthquakes are also going to give us evidence. Okay? Yes, earthquakes, again, create waves. I know, I didn't ever want to talk about waves again, but these aren't as bad. There's not as much you have to know about these. And these waves are recorded. Geologists study how they travel through Earth, because if an earthquake is felt here, there are aftershocks, and again, these seismic waves that can travel through a medium, like the crust and mantle, and even core, and be felt on other places or register on other seismographs in other countries and areas. And the speed of these waves and the paths they take and all the different places that they're registered, that also gives us clues as to what our planet's internal structure is like and what's going on there. They can reveal areas where the makeup or form of materials changes. Because if you remember the definition of refraction, it is when the wave bends due to a change in speed of it interfering with a different medium. Okay? Particularly a different state of matter. Our crust is a different state of matter than our mantle. Our mantle is different states of matter than part of our core. Okay? So we put all these little puzzle pieces together to come up with these ideas. And give the best hypotheses that we can. So here again shows you some ocean waves traveling, and when they hit an object or a different state of matter, how they can bend and refract and change their path or direction. You could think about this as a cross-section of Earth, where you've got the crust, the mantle, the core, more mantle, the other crust, and seeing how the shock waves of those earthquakes are being registered on other seismographs. We are going to stop here before we get into our structure, because as you can see, there are lots of these little planets popping up around here. You don't have to worry about this stuff. I'm only going to be stressed out about this. But you've sat here for almost 30 minutes, which means I've talked more than enough time for you to soak all of this in. Hopefully stay tuned for the next part, and this video wasn't too terrible, but hope you're doing well, and see you in the next one.